Okay, so we're introducing student t distributions, which are important because we need them for the sampling distribution of a sample mean. So let's actually say that. So this is an example of a sampling distribution for a mean when we fail two specific conditions, right? So we don't know the underlying standard deviation of the population, and n is less than 30. We can have student t distributions with a larger degrees of freedom, but for the purposes that we're talking about in this class, larger than 30, we can just use the standard normal distribution instead. So what do these look like? I'm going to draw a representative probability density curve. They look sort of like this, where it is a bell curve shape, but it does have a fatter tail. The mean of a student t distribution is always 0. And we also denote the random variable for a student t distribution by u. Okay, so we'll use capital U here. And in this case, I've drawn degrees of freedom equals approximately 5. So the degrees of freedom is always a whole number, so the parameters are always whole numbers, and each student t distribution is determined by its degrees of freedom. So as n gets larger, though, so as n increases, student t distributions get closer, and this is a very imprecise word here that I'll clarify in a second, to standard normal distributions. So if you took like n equals 100, that's more than enough to say that's basically the standard normal distribution. So to clarify again, what we mean by get closer to is approaches z in probability, which means that the probability of any event for this random variable will be more or less the probability that corresponds to the standard normal distribution, z. If you have a TI-84, you'll be able to use functions like, so in a TI-84 and an 83, but you're less likely to find the inverse function, but you can use TCDF to find probabilities in areas. You'll be asked to give the specific value for or what we would call a z-score, but it's a t-score. So you'll be finding something like, maybe this is negative 0.5, and you're interested in finding this area. TCDF will find that for you. INF-T, on the other hand, and you may or may not have this function. You may need to download it if you have a TI-84. This will give you critical values. T sub alpha. In other words, if you're trying to find where can I determine the top 5% of the distribution, so T 0.95, you can use INF-T to find that value. So for more on these functions, go to the appendix, or you can also use a cumulative density function table for t distributions. So just like as there is for the standard normal distribution, you can find a table that gives you the cumulative density function for a t distribution with a given degrees of freedom. So here's our payoff, though. Remember that we said, so in a previous section, we talked about, or not section, video. We talked about that if we have the random variable sample mean I'll abbreviate RV for random variable, with our sample sizes not being large enough, and from a distribution with known mean but unknown standard deviation, population standard deviation, then we would say, so U being the sample mean minus the population mean divided by the sample standard deviation divided by the square root of n has a t-distribution with degrees of freedom n minus 1. So I want to point out some things about this random variable. So this is the random variable that has the t-distribution. This is the sample mean. This is also a random variable. This is the population mean. This is a parameter. Here we have the sample standard deviation. And here we have the sample size. Everything except for the sample mean on the right side of that equation is a number. It is a fixed number that's determined from the specific scenario that we're talking about. So to see how we're actually going to, work with this, I have an example where we're going to get to explore working with the with t-distributions. All right, so this example comes from a study, and this is a simulated study. This is not real, but we suppose that there's a psychologist that's taking small random samples of attentiveness test scores. So the idea is to examine a link between two different variables. So regular access to smartphones at home how does that relate to attentiveness in the levels in children? And to properly design the study, then there should be a control group and a treatment group. So we have then, from the results of a survey, we have two groups, which are our treatment and our control, no access to smartphones at homes, and regular access. And we obtain these sample means, sample standard deviations on the attentiveness level, or on tests that are administered for attentiveness, and a sample size. So the first group, the no access group, there were 13. The second group, there were 17. So all told, there were 30 children that were tested. And the mean of the first group, the no access group, had 43.2 as the mean score. The second group had 38.4 as the mean score. The sample standard deviation for each correspondingly is 5.4 and 7.8. So because this test, it may not be standard, it may be specific to that study, we don't know what the population standard deviation might be. But we know, for instance, maybe, so suppose we know that X, being attentiveness test scores, are approximately normal with a mean mu of 40, but we don't know anything else about it. So we don't know the standard deviation. We just know it's normal and has a mean of 40. We do have two estimates for the sample standard deviation, so we might need those. And the idea then is that for children without access to smartphones at home, that the random variable u equals the sample mean minus 40 divided by 5.4 divided by the square root of 13 can be modeled using a t-distribution with degrees of freedom 13 minus 1, which is 12. So our question now is, what's the likelihood of getting a sample mean greater than the sample mean for the no access group in the trial? So what's the probability of finding a sample mean that is greater than or equal to that 43.2 in that group? So the probability that we get something larger than 43.2. So let's pause for a second and let's make sure we understand everything that is in play. So first we have our sample mean, random variable, and we're trying to make an inference about this sample mean. We're trying to understand probabilities associated with it. Now, specifically working with this sample mean, we can't do anything with it. But if we standardize, it's no longer standardization, but it is a similar process where we transform this so that we have a statement involving u. Then we can make inferences using the t-distribution. So, to wit, our specific u value is the 43.2 minus 40 divided by 5.4 divided by the square root of 13. And that is approximately 2.136. So this is the value in the support for the standard t-distribution, student t-distribution, where we now want to understand that the probability of this original event, that the sample mean for this group of children is greater than or equal to the 43.2, we've now converted this to a question about the probability that a standard t-distribution will spit out a random outcome greater than or equal to 2.136. And we can use the TCDF function if we want. Just make sure you use the proper degrees of freedom. And we obtain that this probability is 0.0270. So we have a 2.7% chance of obtaining a sample mean greater than or equal to this value. In other words, if we're looking at our, let's not do that. Let's use a different value or a different color. This is our t-distribution, roughly. So, mean of 0. This is u. And our specific 43.2 value, which has a corresponding t-score of 2.136 gives us this tail region here, which is equal to 0.0270. And so we can think of this then as being associated to, or basically being a transformation of this being the mean, the 40, which is the mean for our sample mean. That this is a stand-in for the sample mean distribution, and this is a stand-in for the random value of the sample mean that we specifically got in this trial, the 43.2. Nothing else changes though, because now we have the power of being able to use the student t distribution to find probabilities.